Let's now learn some of the techniques to reduce the power consumption. Such techniques are available at both hardware and software level. In hardware techniques, we will talk about clock gating and power gating. And on the software side, we will talk about operating system's sleep modes and dynamic voltage and frequency scaling, DVFS. So first, clock gating. In the previous video, we saw that digital circuits change their state only when the clock is active. That means usually either on rising or the falling edge of the clock. The idea of clock gating is that if a circuit is not in use, that means we are not doing anything useful with the circuit, just disable the clock to that part of circuit. And this is how we can do that. So this is a flip-flop which is clocked, and instead of directly giving the clock to this flip-flop, you pass it through an AND gate with enable signal. So if this enable signal is disabled, it's 0, the clock won't pass here, this line will always be 0, and there will no activity happen inside this flip-flop. So how would it affect power? So we know that the dynamic power is given by this equation. If we reduce the frequency to 0, we are not clocking our flip-flop, that means the dynamic power will also become 0. So that's how, by disabling the clock to a digital circuit, clock gating saves dynamic power. How about static power? Does it reduce the static power as well or not? Just take a moment and think about it. Well, static power is independent of the frequency. As long as your circuit is connected to the power supply, there will be leakage and there will be static power consumption. To avoid static power consumption, we have power gating. So even with the 0 frequency, the circuit still consumes some power, which is leakage power. So how do we reduce this leakage power or eliminate this power? Well, the idea is that if you realize that a circuit is not going to be used, just turn off the power supply to that circuit. If there is no power supply, there won't be any dynamic power consumption. Also, there won't be any static power consumption either, because if your transistor is not connected to power supply, the current just cannot flow anywhere. So this is how we do this power gating. You have already seen this circuit before. This is a CMOS transistor, this is the PMOS device and MOS device. The only difference here is, earlier we had this node connected to the power supply. Now this is connected to a virtual power supply. So we have this sleep transistor here, which is connected to VDD. So when we decide that we want to power gate our CMOS inverter, what we do is we will enable this sleep signal. So this signal will become 1. And if this signal is 1 for a PMOS device, this device is off. So this node is now disconnected from this node, and this node will eventually discharge to the ground through these transistors, either because of leakage, mostly because of leakage. So when this node has discharged, now the inverter is effectively not connected to the power supply, and there is no static power consumption either. So one of the question you can ask here is, maybe we have disconnected this part of circuit from power supply, but this transistor is still connected to the supply, so there will be leakage here. Well, you're right, but the trick is you make this transistor in a high technology load, because if the technology load is higher, there is less leakage, whereas the leakage increases when we go to the smaller and smaller technology nodes. So sleep transistor is usually in a higher technology node compared to these this transistor that are really doing some useful work. Okay, so this is how, by disabling the power supply to the main circuit, power gating saves both static and dynamic power consumption. So the idea is no power to your circuit, so there won't be any leakage. But this power gating has its own overheads. It doesn't come from free. Well, first thing you have already observed is probably that it needs extra transistors, the sleep transistor. So there is an area overhead. It also has energy overhead, and that's because this sleep transistor we need to turn them on and off. So to turn on and off these transistors, we need to generate the sleep signal and distribute the sleep signal through our chip. In addition, this virtual VDD node also needs to be discharged, that's power consumption, and it also needs to be charged when we want to use our circuit. So that's also additional power consumption. So to get the net benefit from power gating, we need to we should power gate our circuit only when we anticipate it to be not in use for a sufficient long interval. That means that the power saving from power gating should be more than the overhead of putting your circuit in the sleep state and later waking it up. Apart from energy overhead, there are also some performance overheads associated. For example, when you want to use your circuit, you just cannot use it immediately. You need to charge the virtual power supply node to a sufficient level and let that supply level to be stable for a moment, and only then you can use it. So you might need to wait, or you might need to stall some of your operation before your circuit is before you can operate your circuit again. And these both power and energy overheads, they have to be paid every time you put your circuit to power gated state and when you later wake it up. Now to summarize, the idea in clock and power gating is to turn off the clock or power to the circuit when it's not in use. And in a complex chip, there might be multiple clock domains, and each clock domain has its own clock distribution network. And why is that important? Because that would enable that some portion of your chip can be clock gated, whereas some other portions are operating actively with a clock. So that's why you need to have different clock distribution networks in different parts of your chip. Just like clock domains, we can also have multiple power domains, and each power domain has its own power distribution network and power gating circuit, so that you can power gate some portions of your chip which are not in use, while some other portions are working actively. An example can be, for example, if you have a floating point unit in your processor and you are executing integer applications, you can just power gate your floating point unit because you know you are not going to use it and save some power over there.